All right, so today we're going to do a deep dive into something pretty crucial, I think, for anyone who really wants to make sure that they're building applications that are not only correct, but also, really efficient and scalable, especially as the amount of data that they're handling, just keeps getting bigger and bigger. And we're going to focus on, how to avoid those kind of moments when your app starts to feel sluggish, like it's, wading through molasses. And for those of you out there who are maybe getting ready for a big interview for like a senior software engineer position or something, this is the kind of stuff that can really show that you understand, how to make systems really hum.
Yeah, absolutely. It's not just about getting the functionality right. It's about getting it right in a way that performs well under pressure. So we're going to dig into a design pattern that can help with this called the Flyweight pattern. And you can think of it like, I don't know, like the ultimate sharing economy for software resources. The basic idea is to support like a massive number of what we call fine-grained objects. Things like, if you think about a document, each individual character in the document, or, you were talking about a landscape design application, each individual tree in that landscape. And it supports those efficiently by really cleverly sharing the parts that are identical. And the cool thing is that this isn't just some theoretical concept. This is about building applications that can handle, serious scale without, falling apart under their own weight.
Yeah, and we've got some really fascinating material here that kind of shows this in action, particularly when you look at, how text rendering systems work. So, if you're displaying a really long document on your screen, every single letter, every space, every comma, if each one of those was its own unique object in memory, just gobbling up space, things would pretty quickly come to a screeching halt. So understanding this flyweight pattern, it's really, like you said, it's a sign that you get, this deeper level of how to optimize both memory and processing power.
Yeah.
So let's kind of break this down. What's the fundamental problem that the flyweight pattern is coming in to sort of rescue us from? What's that bottleneck we're trying to avoid?
I think that the core issue is that if you represent every element in your application as its own separate objects, especially when you have a huge number of these elements, it can become really costly. And let's think about that text rendering example again. So you've got a document with thousands of instances of the letter E, right? A naive approach might be to create a new E object every single time it appears. And, if you multiply that across all the characters, all the formatting nuances and so on, it's easy to see how quickly you can just blow up your memory usage. And it's not just memory, it's also that managing all these individual objects introduces a lot of runtime overhead, which slows everything down.
Right. It's like that landscape design example we were looking at. If you wanted to have a forest with, 10,000 trees in it, and each one of those trees was, a distinct object holding all that information about, species and size and leaf color and whatever. I mean, your app would probably just choke on that, or you'd have this logical view like, okay, there's a tree, there's a tree, there's a tree. But the flyweight pattern lets us kind of build this completely different physical reality behind the scenes. So can you kind of walk us through what that physical reality looks like?
Yeah, definitely. So with the flyweight pattern, we can maintain that appearance at the logical level. Like you have all these individual objects, but underneath we're actually sharing a much smaller set of actual physical objects in memory. So going back to the ease example, you see countless E's as you're reading a document. But in reality, there might be just one E's object in memory that all those visual E's are referencing. And this is where the difference between intrinsic and extrinsic state becomes really crucial, because it's what allows it to do this, this illusion of many with the reality of few.
Okay. All right. So we're getting into the nuts and bolts now. So let's unpack that a little bit.
Yeah.
What is intrinsic state, and what is it about it that makes it so shareable?
So intrinsic state is the information that's basically the same across all instances of a particular flyweight. And it doesn't change based on where or how it's used. So it's really the core of the object, the part that never changes. And it's stored directly inside the flyweight object in our character example, the actual character code for the letter E. Its Unicode value. That's intrinsic because it doesn't matter if the E is at the beginning of the sentence, the middle of the sentence, what font it's in, what color it is, that core identity of E remains the same.
Got it. Okay, so it's kind of like the essence of the object, the thing that never changes, that defines its type, and that can be shared across all these, seemingly different occurrences of it. So then what is extrinsic state? How does that differ?
So extrinsic state is kind of the opposite. It's the context-dependent stuff. It's the information that varies depending on how and where a flyweight is being used. And because it's specific to each individual use, it's not stored within the flyweight object itself. The client, the part of the code that's using the flyweight is responsible for providing this information whenever it's needed. So, for example, the E's position on the page, its X and Y coordinates the font that it's displayed in the color. All of that is extrinsic because it changes depending on where that particular instance of E appears in the document.
Okay, so it's almost like we've got the shared essence, the intrinsic stuff, and then all of the variations, all of the unique visual or contextual aspects of it are handled externally. Now, how do we actually manage these shared objects? This is where the Flyweight Factory comes in, right?
Yes, exactly. Yeah, Flyweight Factory is like the brain of the operation. It's responsible for creating and managing all the flyweight objects and make sure that they're shared correctly. So think of it like a central repository or a pool of flyweights. So when some part of your application needs a specific flyweight, say it needs to display an E, it doesn't just create a new E directly. It goes to the Flyweight Factory and asks for one.
Okay, and how does the factory know whether it should actually create a brand new E or whether it should just, hand over one that it's already got sitting in the pool? That's the whole magic of the sharing, right?
Yeah, that's right. So the Flyweight Factory uses some kind of unique key to identify each flyweight. And in our text rendering example, the character itself, like A, B, C, that would be the key. So the factory keeps a collection of all the flyweights it's created so far. This is often called the flyweight pool. And when the client needs a flyweight, the factory first checks the pool. If a flyweight for that key already exists, it just returns that instance. If not, it creates a new one, adds it to the pool, and then returns that. And you'll often see this implemented with methods like, get flyweight, where you pass in the key, or you might see something like create character, where you pass in the actual character.
So the factory is like the central clearinghouse. It's making sure that we don't have, tons of copies of the same thing floating around now. I also noticed in the material that there's this idea of a flyweight interface and then these concrete flyweight implementations. Can you kind of walk us through what those are all about?
Yeah, so the flyweight interface is kind of like the blueprint. It defines what all flyweight objects should look like, and it declares the operations that flyweights can perform. And a key point here is that these operations, they often take parameters that represent the extrinsic state, because remember, that information isn't stored in the flyweight itself, so it needs to be provided by the client. Then you have the concrete flyweight, which is an actual class that implements that interface. So in our text example, the character class, which stores the actual character code, that would be a concrete flyweight. And one crucial aspect of concrete flyweights is that they have to be designed to be shareable. So any state they store internally has to be intrinsic. It can't depend on the context.
Okay, I'm following. So the character object, it's got the E, it's got the A, whatever, and it's got maybe like a draw method or something. But all of the specifics about where on the screen it should draw itself and, what font to use and all of that, that's passed in as parameters to that method. Now, I also saw this thing called Unshared Concrete Flyweight, which sounds kind of like a contradiction in terms. What's that all about?
That's a good catch. Yeah, so while the main idea of the flyweight pattern is sharing, the interface itself doesn't force all of its implementations to be shared. It just provides a structure that allows for sharing. So an unshared concrete flyweight is a class that implements the flyweight interface, but is not designed to be shared. These often act like containers for the shared concrete flyweights. So for example, in our text rendering system classes like row and column, those might be considered unshared concrete flyweights because, each document has its own unique rows and columns. They're not shared. But those row and column objects would then contain and manage the shared character flyweights.
Okay, that makes a lot of sense. So you have kind of like these higher level container objects, and then they hold references to these underlying shared elements. So let's really ground this in that text rendering example. So we have columns have rows have characters. How does the flyweight pattern actually play out in that structure to save memory?
Okay, so in this setup, the character class is our flyweight. And for every unique character that appears in the document, uppercase, lowercase letters, numbers, punctuation, all of that. Ideally, there's only one instance of that character object in memory, and these are managed by our Flyweight Factory. So if you have the letter 10 appearing 100 times in a document, there's still only one 10 object, and this is where the huge memory savings come from. Imagine a large document with lots of repeated characters. You go from having hundreds of thousands of character objects down to something closer to the size of the character set, maybe 100 or so for ASCII characters. Right. And even when you throw in different font styles and colors, the core character itself can still be shared.
That's a pretty dramatic difference. So if the character object itself just holds that core data, the letter or the symbol, how does it know where to actually draw itself on the screen and how to draw itself, what font to use and all that stuff?
Right, so that's where extrinsic state comes back into play. Things like the position of the character, the font, the color, all that. It's not stored in the character object itself. It's handled by the objects that contain the character. So, for example, a row object knows its own position on the page, and it arranges its child character objects horizontally. And when it needs to draw a character, it passes in the position information as a parameter to the character's draw method, and the character uses that information along with its own intrinsic state to render itself correctly.
Okay, so the row handles the where, what about the how, like the font and the color and all that? How do we manage that without, making each character object super heavy?
So this is where we introduce something called a glyph context. And the glyph context is responsible for managing that extrinsic state, especially the font information. And one efficient way to do this is to use a B-tree data structure within the glyph context. So the glyph context keeps track of the current position as it moves through the document, going through columns, then rows, then characters. And the B-tree stores information that maps ranges of glyphs in the document to specific fonts.
So let's say you decide to italicize a word in the middle of a sentence. How does the glyph context and the B tree handle that change?
So operations like setting the font or inserting text, those trigger updates to the B tree. So if you italicize a word, the glyph context adjusts the B tree to reflect that change. And later, when it needs to draw a glyph, it uses the glyphs index in the document to query the B tree and find the correct font. And the cool thing about this is that font changes are usually pretty rare compared to the total number of characters. So the B tree stays relatively small, which helps keep things efficient.
That's a really elegant solution. All right. So we've seen that the flyweight pattern can lead to some serious memory savings. What are some other advantages of using this pattern? And are there any kind of downsides or trade-offs we should be aware of?
So one big advantage, as we've already discussed, is this huge reduction in the number of objects, which means less memory used, which is super important when you're dealing with massive data sets or, complex user interfaces. It also centralizes the management of state, which can make things easier to control. And if you have a lot of instances that can be treated the same way, you can potentially get some performance gains by operating on fewer objects. But there is a trade-off. The main one is that once you've implemented this pattern, the individual logical instances, they can't behave completely independently anymore if that behavior depends on the shared intrinsic state. Because if you change something about the intrinsic state of a flyweight, it affects all the instances that are sharing it.
Yeah, that makes sense. Like if all the U's are pointing to the same object and you change something about that object, it changes everywhere.
Exactly. And there can also be some runtime overhead involved in managing the extrinsic state. Things like transferring it, finding it, computing it every time you need to perform an operation. But in most cases where this pattern is a good fit, the memory savings outweigh those costs, especially when you have a lot of intrinsic state that can be shared and the extrinsic state can be managed efficiently.
All right, so we talked about this B tree being used for the font information. Can you maybe expand on that a bit? Why is a B tree a particularly good choice for that kind of data?
So B tree is a self-balancing tree structure, and it's really good at searching, inserting, and deleting data. And that's important when you have a lot of data, like in a long document. And in this context, the B tree lets you organize ranges of text, and their associated font styles, the internal nodes of the B tree, define the ranges, often using character indices, and the leaf nodes store the actual font information, like the font name, the size, the style. And then when the system needs to figure out what font to use for a character, it can quickly search the B tree to find the right information.
Got it. Okay, so when is this flyweight pattern, really the right tool for the job? What are the things that should kind of tip you off that this might be a good approach?
So there are a few key indicators. First, you need to be working with a large number of objects. Second, those objects should be using up a significant amount of memory. Third, a lot of the object's state should be extrinsic, meaning it can be moved outside the shared object and managed by the client. Fourth, for year. You should be able to represent many different groups of these objects with a relatively small number of shared objects once you factor out that extrinsic state. And finally, and this is really important, but you shouldn't be relying heavily on the unique identity of each object, because with flyweights, if you check if two objects are the same, you might get a surprising result since they could be sharing the same underlying instance.
Right. So you have to make sure that sharing those objects isn't going to break any part of your code that's assuming it's dealing with totally distinct things. Now, the material also mentions that the flyweight pattern is often used together with the composite pattern. Can you talk a bit about how those two work together?
Sure. So the composite pattern is all about representing these part-whole hierarchies. Like a document is made of columns, columns are made of rows, rows are made of characters, and when you combine these two patterns, you often end up with flyweight objects as the leaves of the composite structure. So the individual character objects would be the flyweight leaves, and because they're shared, they typically don't have a direct link back to their parent in the hierarchy. Instead, any parent-related information that the flyweight needs is passed in as part of its extrinsic state, so it stays independent of its specific location in the structure.
That makes sense. You don't want those shared elements to be tied to a specific parent, otherwise you couldn't share them as effectively.
Right.
So to wrap this all up, what's the big takeaway about the flyweight pattern that someone going into, a senior level software engineering interview should really walk away with?
I think the main thing is that the flyweight pattern is a powerful way to save memory when you're dealing with a lot of very similar objects. And the key is to understand that difference between intrinsic state, the stuff that can be shared, and extrinsic state, the stuff that varies with each use. And by managing that intrinsic state centrally with a flyweight factory and making sure the extrinsic state is provided when needed, you can dramatically reduce the number of objects in your application, which leads to, big improvements in performance and scalability.
Absolutely. And it's not just about being able to define the pattern. It's about knowing when it's a good fit, what the benefits are, what the trade-offs are. So for those of you listening who are getting ready for those technical interviews, here's something to think about. We talked about text rendering, we talked about landscape design, but what other kinds of applications or systems could benefit from this flyweight pattern? Think about places where you have many similar things that share some core data, but also have unique variations. Thanks for joining us for the deep dive.